Anyway,
The Delta formation in Nigeria and stuff like that.
Yeah.
I like that. Yeah.
hello everyone. This is lecture 12 of PTRE 465531. Last time we made it to, we went a little bit fast through 15 slides who were a little bit overwhelming. We talked about constitutive relationships and we started putting everything. We went from a force balance in each direction, principal direction, to a matrix version of a matrix notation, a tensor notation. We started putting a lot of equations together, and there was not a mistake, some confusion I made accidentally, because both terms have ACC in their how they start. So this is the acceleration term. This is the accumulation term. So acceleration is the one that has the A alpha whatever. Oh, and another way to show it is here. Acceleration term, accumulation term. Remember, accumulation is with respect to time, always. And when you hear something is steady state, all accumulation goes to zero. All accumulation terms should go to zero. So that's something I wanted to clear up. I watched the video and tried to go over what we did. If I went over something a little bit too fast. And then we said that this is basically, it's good for all this stuff. Where is it? We said they are good for rocks, small deformations in rocks. So for small deformations in rocks, they are linear elasticity is an okay. It's not an amazing model, but it's an okay model. And given that it's very easy to apply it, it's the easiest constitutive model to apply, we will go with that. But we said in real life, rocks have what we call anisotropy and what we call heterogeneity. And I went through that a little bit fast. I need to explain them. So heterogeneity means if I go from one place in the rock to another, I have different properties. I have different properties where Malek is sitting than where Hakim is sitting, etc., etc. Now, anisotropy has to do with tropos, means way in Greek, with direction, basically. Similar to direction. So if I'm looking at one direction, I have one value. If I look at a different direction, I have another value. And it goes on like this. And so there are both degrees of complexity that I might have in the rock that my model will struggle to incorporate. So I wanted to explain them. Today we will assume isotropy and do some simplifications to make our life easier. And then we make it a little bit more complex after that. But we also went through two mechanical properties. The Young modulus, which is basically I apply a force on my material, I extend it in the direction that the force is applied to, and then I get a measure of the stiffness, and the measure of the stiffness is Young modulus. And we said that the stiffer the material, the higher the Young modulus it will have. And the Young modulus is dimensions of pressure. And then we talked about another one, and we do have upcoming example problems that will help you understand how these are calculated. But Poisson's ratio, and you should already know from solid mechanics, is basically dimensionless and says, okay, if I elongate, just like chewing gum, I elongate a piece of chewing gum, it becomes narrower, right? I compress a piece of chewing gum, it becomes fatter. The change in the displacement cost, displacement in one direction induces displacement in the orthogonal direction, is given by Poisson's ratio, which is dimensionless. And even though the name is Poisson's ratio, it's still a modulus, because we say that linear elasticity, if I assume that my model is linearly elastic, there is 6 moduli that can be used to characterize the way it behaves, stress versus deformation. Out of those 6, the way that they are interconnected with each other, you only need 2 to get the other 4. 2 moduli,
Okay.
and you get the other 4. And generally speaking, Young modulus and Poisson ratio are fairly easy to measure in the lab and very easy to understand physically what they mean. We are going to see the remainder 4. But it gets a little bit more complex. It has to do with wave speed through the solid and stuff, other stuff. But Young modulus and Poisson ratio, I think you need to know physically what do they quantify and be comfortable with it. So now we did say that they are what do we say? Okay, it's there is anisotropy, so X different in X, different in Y, different in Z. And then the way that those properties are arranged are such that you end up with a 9x9 matrix tensor. So you have 81 values in it. That means if you have one core, you have to make 81 measurements for each property. 81 times whatever, and you have a lot of sort of complexity, associated errors as well. It becomes a mess. And this guy, Voigt, he was a mathematical physicist, German. A musician was he amateur musician. Like
Pianist as well, I guess.
yeah, but he was a Bach guy, whatever Bach was. Pianist.
But it's like kind of one of the complex melody they do in the orchestra. You know?
Oh.
German melody.
Oh, okay, that makes sense.
Oh, yeah.
But he was a chair of a department. He was like a big guy in academia. So like music was his hobby. So he came up with a way to notate this. Actually, this guy is the guy who, when we say tensor, what we mean by saying tensor came from this guy. And he said, look, out of those, you have 9x9 matrix, but not all of them are completely independent. So you have 81 components, but some of them are related to each other. So I can reduce it by assuming isotropy to 6x6. So I can put everything into 6 equations and set it up like this, if there is isotropy. That gave the idea so that in rocks, you have a lot of times this situation where it's basically a system where you have layers, and every layer has a different set of properties. Here you have X, here you have, I don't want to use English. This is layer A, layer B, layer C, D, E. Okay, if I'm at layer C and I look around me, I see the same properties. But then I move to layer D, I look around me, it's different properties than C, but they are the same around me as long as I'm on D. So it's like I'm in different floors.
Which floor is painted with one color?
Yeah, every floor is painted with one color, exactly. So I'm looking the same color in every floor. In every floor has one color.
Horizontally, but
yeah, but vertically is different. Yeah, a lot of rocks have this exhibit this behavior. Shades too. The barnet is tilted down its vertical layer, but these are very, very useful, then you have Voigt's notation can be good for each layer. It helps simplify things by assuming isotropy. And then even if you have anisotropy, it's not useless. You can still use it a certain way. But yeah, he put together basically tensor as we know it is, it was his concept. And yeah, isotropic. Let's assume that E and μ, Young modulus and Poisson ratio is the same in every direction. So I have isotropy, and then I'm left with three equations for the normal strain. The normal strain is the x in the x direction is the one induced by sigma xx, it's normal to it, times the Poisson ratio of what is induced by the sigma yy, which acts perpendicular, minus the Poisson ratio times what is induced by sigma zz. So basically, I have epsilon xx is equal to epsilon xx minus epsilon yy minus epsilon zz. And
The two epsilon is all the same, or they are
that's basically the no, it's the component.
That's from the first equation that E equal to sigma divided by the deformation, the strain, stress by strain.
Yeah, but that
That's key.
material
That's-
material was unconfined on the sides, right? So everything on the sides, you have epsilon yy equals 0, and epsilon zz equals to 0.
just
So
like
those
the-
go away. Now, if you are confined on the side, imagine if this is confined, I'm applying a stress like this, the walls are holding it together, so they are applying
Yes,
stress on the lateral direction. I need to take account of that too. The earth is like this, you have the other vector, and you are confined.
Yeah.
So you get
Boundaries,
you get the tectonic stresses from the sides. So you have that, and you have it in all three directions. And you will see why you have, it looks like you have two epsilon xx, but when you arrange them in a certain way, it's gonna be more understandable. Shear strains now, it's a little bit more complex. And we're gonna use a new modulus, which take it as I give it to you right now, but it's a very common, the 2 pages of derivations to get into it, but what we call the shear modulus of elasticity is basically the Young modulus divided by 2 times 1 plus ni, in parentheses, or E divided by 2 plus 2 ni. And they are given by this. So you have and notice here they are shear, all of them are shear. Some of them use gamma here, and they use tau here. So you may read it from a book like, whose book? Like Fire's book from 2007, Petroleum Related Rock Mechanics. I believe he uses this notation. Something like that.
They use kind of lambda instead of.
Lambda is something else. Lambda is the Lamé first parameter. We're gonna look into that.
It's the direction of.
Unless they use the capital lambda
Yeah, capital lambda.
with the
Yeah, it's like.
lambda. Yeah, triangle sort of.
No, but it has like kind of cube.
That's for something else, I think. Do they use shear modulus?
It's for a strain direction, something like that.
Okay. I know they use lambda, but the capital lambda. It might not be Fire's book. It might be another book.
No, other books.
Oh, okay. Yeah, many people use gamma and tau for that. So don't get confused. Yeah, go ahead.
For example, structural geologists use sigma for principal stresses and tau for shear stresses.
Yeah, that's what I was saying. But for us, it's very, if you use sigma for all stresses, all effective stresses, then if the subscripts are the same, you know it's normal stresses. And then if here the subscripts are not the same, so you automatically say, oh, shear in both of them, right? Not normal.
X, Y, yes.
Yeah. They are not the same. So these are the remainder equations that you can get from this shear modulus. Now, how about we combine them? We have 3 in the previous slide and 3 on this slide, and we put them together in a tensor. We combine everything together, and we have a stiffness matrix. So we are going to have the same equation as we had before, sigma proportional to strain, E epsilon. This sigma proportional to epsilon, but because it's in all directions, I cannot use E, right? I need to do something three-dimensional. So I am using tensor, and I am doing this. I arrange them in the way that Voigt like. The first, the normal, and then the shear, and then I have the stiffness matrix, and then I have the induced strains. And notice there is. So all these, sorry, oh no. This is the stiffness matrix C. Okay, so for the entire continuum like one mass, REV, for instance, if you are modeling with finite volume, this is the stiffness matrix. If I'm isotropic, that means E is the same X, Y, Z direction, me is the same X, Y, Z direction, and yeah, I only need 2 to have what I need. So I have sigma XX, sigma YY, sigma ZZ, sigma YZ, now it's the shear, sigma XZ, sigma XY, and the corresponding strains on the other side. And if you are using MATLAB and you are trying to solve this equation, as long as you set this matrix right, you basically do, what do you do? AX, you have basically something like AX equals to B. So now you want to solve for what? You want to solve for X. No, for, yeah, you do like X is A, B. You use the backslash.
That's in MATLAB, but if you want to do it, it has to be multiplied by the inverse of A.
Yeah, you need to do,
A minus 1.
or there are many ways you can solve it. It's basically numerical method. You can do Gauss elimination, LU decomposition,
yeah,
a lot of stuff.
But mathematically, it says to be multiplied by A minus 1 in both sides.
Yeah. You get the inverse. Yeah.
The inverse from the left.
And we're going to talk about the inverse of the stiffness matrix.
So that division is a MATLAB division.
Yeah, and it is not always stable. This command in MATLAB, the matrix, if it's not diagonally, what we call diagonally dominant, it gives you an error, and that error, if you use it many times, it truncates to a bigger error, and it's what we call a truncation error. You end up in the finishing a simulation with a big error. You need to be very careful. Normally, people, when they use this, they have a condition in their code. They condition their matrix before it gets into this command to make sure that it's correct, diagonal indominant, what we call diagonal indominant. And what we do, well, in the reservoir simulation, you use that command. You can use that command a lot, but it used to be much faster than, say, doing LU decomposition. But you can write a code in MATLAB, a function file, to do LU decomposition for you, and maybe make it go faster, you know? Okay, so we talk about correlating sigma to epsilon using the stiffness matrix. Let me ask you a question that somebody asked in Texas, a Chinese student who was going for this defense. He asked him, what is and the Chinese student knew the answer. What is the antonym, which is the opposite of stiffness?
Softness.
No. Close, no, very close.
Yeah, it's like,
If it's stiff, it's hard to.
So hard and soft, stiff and compliant. Yeah, compliant. But soft is a synonym of compliant, if you think about it, in qualitatively at least. Okay, so if we inverse the stiffness matrix, we will get compliance matrix, right?
if you reverse it,
Inverse.
yeah.
Inverse is like it needs to add up to, but if you multiply one with the other, you need to get the identity matrix.
Oh, so the function, the inversion,
Yeah,
function inversion.
in INV in MATLAB. Now, if you inverse it, you get and sometimes
Kind of exponential logarithm.
it's much easier to do it like this. Many times the compliance matrix is easier than the stiffness matrix to deal with mathematically or arithmetically at least. It's the same thing, it's just got reverse. And now I have epsilon equals d sigma, whatever, sigma, yeah, sigma, this one. And again, I can use that AX equals to B, X equals A/B command hypothetically or potentially, but it's the same set of equations. I just calculate strains from stresses. So, you see from those two slides, you go from stress to strain, and from strain to whatever, to stress. But in a model, if you model a continuum, like REV is a continuum, right? It's a mass. It has this. Everything has this. Now, if you model a system that has many of these, you have many of these, and they are all dependent on each other, right? So it becomes, there is a continuity, and the continuity is basically with the Cauchy's laws. It's starting from Navier-Stokes momentum balance.
Like find elements when you do simulation.
Well, it depends on, you can do finite volume, you can do finite element, you can do finite difference. For fluid flow, finite difference is much easier for fluid flow, but this is for stress, yeah.
They do material balance.
Yeah, but structural analysis, you need material balance.
Mass balance, those stuff, yeah.
All those all together in a sense, but structural analysis, Plug 3D is a boundary element system. So for one boundary element, for one REV, you have one value of everything.
Exactly.
Yeah, something like
For
that.
example,
Actually, it asked me that in my proposal. They asked me the difference between finite element, finite volume, boundary element, because I had simulations and geomechanics. Yeah. When was it? November 6, 2018, Tuesday. I went to Buffalo Wild Wings after I finished. Buy one, get one free. No, it was Tuesday.
Tuesday, yeah, Tuesday.
Yeah. Wednesday is all you can eat here. Yeah, but not there, not in Louisiana. Anyway, so now that any questions on the previous slides? Okay, so I guess we can proceed. Well, there is no online audience. If you have any questions, email me. If you think I moved too fast, go back and look at it again. But basically, it's you try to relate strain to stress and stress to strain. Now we are gonna look at the remainder of. We have 6 equations, right? Right. So, we have 6 equations. So it makes sense if I have 6 equations, how many unknowns I can solve for? 6. So, okay, 2 unknowns we know, Young modulus, Poisson's ratio. There is 2 more right now, the Lamé parameters.
And do we know shear?
Well, we know shear, and then there is another one coming later, the bulk modulus.
Yeah, both.
Okay. So we're gonna see the remainder. So, what about Lamé? Another name on the Eiffel Tower is on the other end. Couch is on the left side, and then Lamé is on the right side of that sort of line, not the same line. But you know, every side that you see, it has a series of names. Couch is the first one on his lane.
He was, Lamy was, I guess, the geotechnician or something like that.
He did apply a lot of, he was also another guy who went from application to theory. He did a lot of work on cannons, like guns, like weaponry, I guess. How much you can load a cannon without exploding. A lot of that. He must have done, I don't know if he did structural analysis, but he was also doing theoretical physics stuff. Lagrange is also on the Eiffel Tower, I think. And Lagrange is Italian.
Lagrange?
Yeah, he was Italian and moved to France.
Lagrange is French.
But it was a different name in Italy. He changed it to, I think he was.
They changed his last name.
I think he was. He may have been born in Italy, but from French parents. I don't know. Maybe. But I know a lot of it was during Napoleon's time, so it depended on which side you are. So there was a lot of, like, if the other side wins the elections or wins a war, you have to move your job and go somewhere else and then come back. It was a little bit like that.
The Republic in France.
Yeah. It was before in the 1700s, must be 1700s. Yeah. So that about Lamé. He came up with 2 parameters to use instead of epsilon, E, and Mi. So if you don't want to use Young modulus and Poisson's ratio, you can use his other 2 parameters, which are lambda, the Greek letter lambda, Mi times E divided by 1 plus Mi plus times 1 minus 2 Mi, or M sometimes it's used by the Greek letter mu. Now, unfortunately, in this class, we have a different definition for mu. And if you take a reservoir, there is a different definition for
it's
mu.
not viscosity, yeah.
It can be viscosity, it can also be the friction factor between rocks, faults.
Exactly.
This is not the same mu. That's not the same mu. This is not the friction factor. No, this is a mechanical parameter.
Because the regime, you will know how much it displaces in the fault.
No, that's the friction.
Yeah.
Dimensionless friction. No. This one has units. This one has units of pressure, dimensions of pressure. This one also, they both have dimensions of pressure. This is a different, completely different parameter. It's a mechanical parameter. It's not the same as the, what's his name? The one that, forget him, 1979, Barley. It's not like the same as Barley calculated. Not the same thing at all. This is a mechanical parameter. And it has to do, you can measure them in the lab if you get like T wave and S wave velocities.
Yeah.
It's much complicated to explain what they mean physically, and even more complicated to explain how they are derived. but there is a lot of material online that can guide you. And it depends on who was teaching your solid mechanics class, if you're an undergrad, if they went through the derivation or not, it can get pretty difficult. There is a lot of assumptions involved, but there is some more parameters. So now we know 4 parameters, so 5. Okay, we know epsilon, ni. We know E, ni, lambda. I use capital M. Some people use this for, it's called Lame's first and second parameter. And the thing is that in the Greek alphabet, lambda is before mi.
Like his name.
Oh, I didn't think about that.
Lambda and the new.
Yeah. So lambda mi.
Lambda.
So lambda is the Lame's first parameter, and M is Lame's second parameter. In this class, I will use, just like I believe in Zobak's book, if I'm not mistaken, we use capital M to explain it, to denote it. Sorry. So now we know 5 really, because we also know K. Sorry, G. I forgot I was underlining to write how many do we know. We know E, we know ni, we know
Lambda.
G, we know lambda, and we know M. Yeah. So 5. 6 equations though. There is one more. One more coming. Now if I want to, yeah. But how does my equation simplify with those? Become like this. So you can arrange this into the matrix. Instead of having epsilon and mi, you have lambda and m. If you want, you can do that. And that is stupid for me. I made a mistake here. I don't know how nobody caught it last. Yeah, look at that. This should be m, not mu. This is M. I will fix it and upload. Yeah.
But it's maybe there.
Yeah. But later on in the other module, that mu will come as a friction factor between the rocks. It's very confusing if you say for this module mu means one thing and for that module mu means another thing. And the students come from reservoir, mu means viscosity. Well, in some papers that we have mu and friction factors, we just use eta for viscosity. Yeah. Anyway, yeah, that's basically the equation. Again, 6 equations, 6 unknowns. Clearly, I think you understand that the unknown is either this, and I know this. Or the other way around. I get this 6, and sorry, I calculate this from this. So 6 on each side. I can go from one to another set. So this can simplify the expression of Voigt to the following. As you see now, I don't have the mu here, the m here, I have it here, right? And again, it's the same thing. It's the stiffness matrix, right? But it's given in different pair of inputs. Yeah, it's like, okay, how did you measure? What did you measure in the lab? Maybe you are not able to measure lambda and m. You are only able to measure epsilon and mu. What if you measure epsilon and lambda? What if you measure epsilon and m?
Yeah.
Everything is possible. And remember what I said in the beginning of the class, You need 2 to get the other 4. It doesn't matter which 2, just as long as you have 2. And let's see the last one. We have time. Bulk modulus. Okay, this is a little bit, I leave it at the end because it's a volumetric property. So it requires a little bit different kind of thinking. You need to think about it volumetric wise. Changes that happen in terms of volume. Like you need to think of it as the whole REV changing. Not like in one dimension. It's a little bit more complex to understand, but it's actually more useful. We are going to see later, qualitatively speaking, or quantitatively speaking. So it's the ratio between volumetric stress and volumetric strain. So I apply a volumetric stress and I get a volumetric strain. So these are 3-dimensional stuff. It's associated with the change in the volume of the body and determines how much the body will compress under a given amount of externally applied stress. This looks a little bit more complex, but it simplifies to this, okay? This is I applied a change in the stress and I got a change in the volume. And I divide the change in the volume by the original volume. And then I have the change in the stress in the numerator. Now this is for a general material. Okay, a general linearly elastic material. For us, rock people, it can translate to change in permeability, porosity, versus the original porosity.
Compressibility.
Yeah, inverse of compressibility.
Yeah, inverse.
Compressibility. So if somebody gives you the Young modulus, sorry, the bulk modulus of aluminum, he automatically gave you the compressibility of aluminum.
Yeah.
If somebody asks you to calculate the bulk modulus of aluminum, I had a professor do that to me once. You just go to Wikipedia and find if you want to calculate the bulk modulus of aluminum, you go to Wikipedia and you find the compressibility of aluminum and you inverse it.
Yeah, 1 divided by, yeah.
So the units would be 1 over pressure. The dimensions would be 1 over pressure. Let's just say 1 over PSI. In oil field or SIP. In oil field or in the office, I guess, of operators or R&D oil field services, they use this unit, they call it, let me write it better, SIP, like sipping tea, for instance.
Like the reverse of PSI.
It's square inch per pound.
Yeah. Or 1 over atmosphere. It can be converted to 1 over
So
atmosphere.
pressure square inch becomes square inch per pound.
Yeah. Per pound.
No, it's pound per square inch and then it becomes square inch.
Yeah.
I mean, that's what PSI means, pound per square inch.
Yeah.
Absolutely. And it's pound force, not pound mass.
No power force, yeah.
Yeah.
It's the F, yes.
Yeah, LBF, yeah. Any questions on the bulk modulus? But you guys need to understand that it's a 3-dimensional consideration here. I have a box, my REV. I should have drawn it red, but okay. Oh, by the way, I was wrong in what I wrote. The bulk modulus is pressure. The compressibility is inverse pressure, right? So this one here, if I was proper, this is PSI. Okay, compressibility is SIP. That's why, but in the office, in an applied job, it's better to talk about compressibility than Young modulus. Right?
The compressibility used to like give the symbol of C.
Yeah.
And C here you have the stiffness.
Well, C small,
Yes.
and the stiffness is C big.
Ah,
And you have CW for sea water,
see what,
sea oil, sea,
Yeah.
formation, whatever.
gas, compressibility.
Yeah, a bunch of stuff. So remember we have, let me use green since my REV is green.
No, yeah.
Yes. Okay, I applied stress and I cause this displacement. Wrong. Put así as
Share your screen.
okay, screen sharing.
Share your screen.
No, this is another.